Hi guys. I'm sorry it's taken me so long to get this lesson up. The district changed something about the way we download our programs and stuff, and so I haven't been able to open my screen recorder for the past couple of days, but I was finally able to get everything figured out, so sorry about that. Lesson 63 part 1 we have already gone through in a different video, and that is our t distribution. So when we do a confidence interval for a mean, I guess you guys might want to see the paper instead of me, sorry about that. When we do a confidence interval for a mean, we have to use a t distribution instead of a z distribution. Let me see if this is one of the completed papers. A few of the biggest takeaways from that video are the following. So we have to use a t distribution because we don't know theta. A t distribution is a normal distribution. It just has more data in the tails. The bigger your sample size is, the closer it gets to a standard normal curve. And to find your critical value, you have to find this thing called the degrees of freedom. There are lots of different t critical values. So for z critical values, there's only a handful, and they're at the very bottom of our pink table. But for a t distribution, there are several different t critical values. Let me find my table really quick. So down here are, on the last row, is our z criticals. And all of these in here are t criticals. The reason why there is so many is because each t distribution has a different shape depending on your sample size. So last video was going through why we use a t distribution instead of a z distribution. So the main focus of our lesson today is creating one sample t intervals for mu. You're going to create one sample t intervals for mu. So I'll go through and fill in these blanks with you. When we make one sample t intervals for mu, we have to check our three conditions. So that's the random condition, the 10% condition, and the normal or large counts condition. Now the first two we're used to and we know exactly how to do them, but this third one creates a lot more work for us, and that's the bulk of what we do in the lesson today. So for our random condition, these are the same blanks that we used for the confidence intervals for a proportion. So the data should come from a well-designed random sample or a randomized experiment. And we haven't really talked at all about experiments at this point. We've basically just been talking about the inference to a population. So if our sample is not random, we cannot make inference about a population. If we were talking about experiments, we would be talking about cause and effect instead of inference to a population. We would be making inference about cause and effect. So we just want to make sure that our sample is random. Second, we check the 10% condition, and it's the same 10% condition we've been checking for last unit and this unit. So it's this guy that makes things a little bit more challenging for us. So two things are happening here. We need to check either that the population is normal, or we need to verify that we have large counts. What we do depends on what our sample size is. So if our sample size is greater than or equal to 30, we're in a large counts situation, and that means that the central limit theorem applies. So that's this bottom bullet point. If our sample size is greater than or equal to 30, the central limit theorem applies, and that says that our sampling distribution is normal. So central limit theorem has to do with your sampling distribution. If your sample size is less than 30, we have quite a bit of work that we need to do, because we need to be able to verify that the population is normal. So this one applies to a sampling distribution. But if your N is less than 30, we have to verify that the population has a normal distribution. So I'm going to make like a little arrow connecting these two. So CLT tells us our sampling distribution is normal, and that allows us to make a confidence interval. If our sample size is less than 30, we need to verify that the population has a normal distribution. If your population has an unknown shape, and is less than 30, then we have to graph the sample data to assess normality. So we don't know the population shape because they don't tell us. In our previous problems, they just told us what the population shape was. And the other issue is that our sample size is less than 30. Why do we use a graph then? If we need to know if the population is normal, why do we use a graph of our sample data? Well, we've often talked about how if we're trying to estimate something about a population, the easiest way to do that is to take a sample because it's quicker and, like I said, easier. We're allowed to take a sample because that sample is supposed to represent the population. So if we take a sample and the sample is right skewed, then that is a very good indication that the population is also right skewed, because our sample is supposed to look like our population. If we get a very nice sample that looks like a normal distribution, it's roughly symmetric and has no outliers, then we can say we think that the population is approximately normal. So I'm going to reiterate that, but consider some of these graphs down below. So each of these represents sample data. This is 8 examples of sample data. So all of these are samples. So where it says determine if it's reasonable to believe that these data, we're specifically referring to sample data. So if you have a sample that looks like this, that is a good indication that your population also looks like this. Same for this one. Same for this box plot. Same for this dot plot. We think that our sample reflects what our population looks like. So we do not use t-procedures if the graph shows strong skew, or outliers. If there's strong skew or outliers, we are not allowed to use a normal distribution to find our confidence interval because we have to use a normal distribution. If our data is not normal, then we can't use a normal distribution. So for each graph, we are deciding if it's reasonable that they came from a normal population. It is essential that you guys understand that what we are checking is whether or not the population is normal. That's so important. So if it's reasonable, I'm going to put a check mark. If it's not reasonable, I'm going to put an X. So down in the bottom left, this one would get an X. This is what you would call strong skew. Some people also refer to it as obvious skew. So strong skew. This guy, he's okay. No skew, no outliers. This box plot right here, I have mentioned before that I prefer box plots. I think that they're one of the best graphs that we can look at, and part of the reason why is because if you have outliers in your data, they show up as points. So these points here on this box plot are for sure outliers. So this is a no. We cannot use a normal calculation on this sample data because of these outliers. And when I say they're for sure outliers, I mean they've been calculated to be outliers using the 1.5 times IQR rule. So they're truly outliers. If you look at the left side of this box plot compared to the right-hand side of the box plot, this is also strong skew. So not only do we have outliers, but we also have very strong skew to the left. The bottom right, he's looking okay over here, but I'm pretty sure that these guys are outliers. I'm not 100% sure, but I'm pretty sure those are outliers. So this would be a no. Top right, this guy looks pretty good. He has, he's not perfect. He has a little gap here. But overall, he's good. Overall, we can use him to do a normal calculation. This histogram, though, is a no-go. Why is this histogram a no? Hopefully you're thinking because that guy is almost certainly an outlier. So with these last two, I want you to pause the video and decide if you think we can use them or not use them. Really use really pause and draw a check mark or an X. Our stem and leaf is a no. These make me feel like they're outliers. I'm not 100% sure, but I'm pretty sure. So I would not use this to do a normal calculation. However, I would use the box plot. 1, there's no outliers. If there were any outliers in this data, they would show up as points like down here. And 2, there's not strong skew. There is right skew. This box plot is right skewed, but it is not strongly right skewed. So there are only 3 that we would say it's reasonable that they came from a normal distribution. The top left, the top right, and this second histogram in the bottom. So to zoom out and revisit, well, I can't really zoom out. Sorry about that. We're checking three things. Random and 10% condition, we're used to. We've done it a bunch at this point. But now, whether or not we can use a normal distribution becomes a much more complicated affair because we need to be able to determine either that the population was normal or that my sample size is big enough that the sampling distribution is normal. It is very important that you are understanding that these are separate. Either you're looking at whether the population is normal, or you're looking at whether the sampling distribution is normal. This case is Gucci. So fast, so easy. This case, nightmare. Such a nightmare. Okay, so our first example is an easy one. Our first example is an easy one. So how do I know that this is easy? Well, we're looking at the distribution of the price of cell phone bills in Utah. They tell us that the population is skewed right, but they also tell us that N, our sample size, is 66. So that means the central limit theorem is going to apply, and it does not matter that the population is skewed right. The other thing that makes this problem a bit easier is that they give us our X bar and our standard deviation of our sample. So all we need to do is add in the element of checking our conditions. So I'm going to go through this faster than I normally would if I were actually teaching this in class, because you guys have the ability to pause the video and write all the things down that need to be written down. So the first thing that we do is create a 95% confidence interval to estimate the mean price of Utah's cell phone bills. So what are we doing? We are estimating the true mu, notice the symbol that we're using there, which is the mean price of Utah's cell phone bills. How do we do this? We are doing a one sample T interval for mu. And it is essential that you write that down. You do not get full credit on your free response unless you indicate the procedure that you're using. I use the formula to check my conditions, but some of you guys in your Can You Do's, you just go straight to the numbers. That's okay. I think that this is better, but I'm pretty sure you would get full credit for just writing out the actual confidence interval, the formula. So the X bar always reminds me to double check my sample was random, and it was. So I just write random sample. Nothing is typed here because you're not required to do this to get full credit. So this reminds me, did this sample come from a random method? T distribution. I'm allowed to use a T distribution because N is greater than or equal to 30, so the CLT applies. This is where I calculate my degrees of freedom. So 66 minus 1 is 65. On our pink chart, there is no 65, so we need to use 60 instead. I find my T critical at this point as well. So a degrees of freedom of 60 and a 95% confidence level is a critical value of 2. So I've checked random, I've checked large counts, and now I'm checking 10% condition. My population is all Utah cell phone bills. So it is reasonable to assume that 66 is less than or equal to 1/10 of the population. And in this case, we don't even need to say it's reasonable to assume. We can just flat out say, if N is all of Utah's cell phone bills, then this is for sure true. We're not assuming that it's true. We know for sure it's true. This would mean that our population is at least 660. There's at least 660 cell phone bills in the mile radius of where you are sitting right now, let alone the entire state. Okay, so random, large counts, 10% condition. At this point, we can build our confidence interval. So X bar is 110 plus or minus a critical value of 2.0 times a standard error of S, which is $27, that was given to us up here, over root 66. You guys pause the video and actually find these values. Pause and really find them. Your lower bound is 103.35 and your upper bound is 116.65. So we are 95% confident that the interval from, use a dollar sign, $103.35 to $116.65 captures the population's mean mu price of Utah's cell phone bills. So we're 95% confident the true average is between $103 and $116. So last part B, is it plausible that the mean is 118? So they're asking, is it plausible that mu could be 118? They're not asking about a range of values, they're asking about one specific value. And all we need to do is determine, is it in my confidence interval? And the answer to that is no. 118 is not a plausible value for mu because it is not in our interval. There are 3 pieces that you have to have for this answer. You need to explicitly say no, explicitly say not plausible, and explicitly say not in our interval. As long as you do those 3 things, it doesn't matter how you word it, what order you word it in, as long as you have those 3 things. So far in this lesson, we have talked about the conditions that we must check. The one that is the most involved is deciding if we can use a normal distribution. If n is greater than or equal to 30, then everything is easy and central limit theorem applies, which you see in this example. This is an easy problem because n is greater than or equal to 30, and they give us our information that we need. So I'm going to stop the lesson here and then start a new one for what happens when n is less than 30. You definitely need your calculator for the last part of this lesson. So this first video is when we have an easy case, and it's easy because central limit theorem applies. Grab your calculator.